Hello again. In this lecture we will learn how research satellites are used to increase our understanding of how our atmosphere works. Research satellites differ from operational weather satellites in that they are often conceived to study particular scientific questions or problems. Sometimes, however, several topics are combined onto a single platform. We will look at one example of a research satellite that we at Chalmers have worked closely with. We will also look briefly at two scientific questions on how satellite data contribute to our understanding. Odin is an example of a small research satellite that was conceived to address the question of ozone loss in the stratosphere. Odin was built in Sweden in collaboration with Canada, France and Finland and was launched in 2001. And it is still operating even though it was originally designed for 2 years of operations. It carries two instruments. A sub-millimeter radiometer, SMR, that is a microwave instrument working at 500 GHz. You can see the 1 meter antenna in the picture. This also gives you an idea of the size of the satellite. The other instrument is OSIRIS, optical spectrograph and infrared imaging system, that is mounted inside one of the walls. Both instruments are co-aligned and are designed to look at the limb of the Earth. To allow us to get profiles of the various gases, the fields of view of the instrument are swept up and down through the atmosphere by wobbling the satellite. The animation shows this, but is of course not to the correct scale. In reality, the satellite only has to wobble 2 degrees to cover the atmosphere from the ground to 100 kilometers altitude. In this manner, we can achieve an altitude resolution of around 2 kilometers. As a first example of the type of research carried out by the Odin satellite, we will look at the phenomenon known as the ozone hole. This was first discovered in the 1980s by researchers at the British Antarctic Survey, and many years of research have gone into understanding why and how ozone is being so dramatically lost during the spring months of each year over Antarctica. The figure you can see summarizes current understanding in a simplified manner. Two sets of processes interact to cause this phenomenon. Microphysical processes involving the growth of a special sort of cloud and chemical processes that interact with these clouds. During the Antarctic winter, there is no sunlight to heat the stratosphere, and so it cools by radiating energy to space. As it does so, vortex winds are set up isolating the air over the pole so that no heat is transported in from lower latitudes and it continues to cool. As it does so, the very small amounts of condensable gases that are present start to deposit on already existing particles and form polar stratospheric clouds. In the picture, you can see an example of such clouds over the McMurdo Base in Antarctica. This process is illustrated in the upper part of the figure. Here you see the gases such as sulfuric acid and nitric acid accumulating to form first type 1 PSC, the short for polar stratospheric clouds, followed by water as the temperature continues to decrease. As the particles get bigger and become type 2 clouds, they can start to fall, removing some of these substances. The bottom row of the picture shows the chemical processes that, in connection with these clouds, lead to ozone destruction. First, chlorofluorocarbons, or CFCs, are brought up into the stratosphere, where they are broken down by the intense UV light from the sun. Remember that, in and above the ozone layer, there is very little protection from the sun's solar UV radiation. The chlorine atoms that are released are luckily bound up in two forms, that is, hydrochloric acid, HCl, and chlorine nitrate, ClONO2. These gases do not destroy ozone. It is first when PSCs are present in the atmosphere that special chemistry takes place, releasing the chlorine. So in the cold winter night, the stratosphere is primed for ozone destruction. First when the sun starts to return can the chlorine start to destroy ozone. This is illustrated by the final loop in the figure. The chlorine converts ozone to normal oxygen molecules and then is reformed to continue to eat up the ozone. In this way, in the places where PSC have been present, the ozone is quickly destroyed. We will now see a film showing how these processes can be observed by the satellite instruments such as SMR and Odin. The maps were created from Odin data ingested into a simple model. The upper row shows the northern hemisphere and the lower row the southern hemisphere. The colours show the amount of the gases ozone, water vapour, nitrous oxide and nitric acid that are present at about 20 kilometers altitude in the stratosphere. The movie begins at the beginning of August 2009 and continues until the end of the year. You can see the date at the top of the picture. Concentrate on the lower row. At the beginning of August, the stratosphere is in the middle of polar night. It is cold and has actually moved downwards as the air gets colder and denser. The region of the polar vortex is seen by looking at the N2O map. The blue values show where the air has cooled and sunk. You can also see low values of nitric acid and water vapour inside this region, indicating that PSC are present. They have been condensed into the clouds. Let us now look at ozone. In August, we see a colour of high values around Antarctica and slightly lower values within the vortex. As time moves into September and the sun starts to return, we see the colours change to darker blue near the edge of the vortex, indicating that ozone destruction is beginning in the sunlit part. The dark colours move inward as time progresses, and by the end of September, nearly all the ozone within the vortex at this altitude is gone. The situation persists until the beginning of December, when the returning sun has managed to heat the polar vortex sufficiently that the vortex breaks up and the ozone-rich air floods back into the polar regions. Now take a look at the whole video again. You will certainly need to play it several times to catch all the details. As a second example, we will look at how we can study the interaction of our sun with the atmosphere. The movie you see was made by NASA's stereo mission and shows what an active place the sun is, with lots of material being ejected, some of which reaches the Earth. This can affect the atmosphere in different ways, either directly if the electrons and protons slam directly into the atmosphere, or indirectly by promoting aurora or polar lights. In both cases, chemicals such as nitric oxide are created, and these can, for instance, affect the balance of ozone in the middle atmosphere. This figure shows the amount of nitric oxide measured by Odin above the North Pole between October 2012 and April 2013. Most NO is seen above 90 kilometers and is produced mainly by the electrons causing the northern lights. Normally it would remain there, but as you can see, in February, a tongue of NO is pulled down into the upper stratosphere. Only satellite observations are capable of measuring this type of event. In this lecture, we have looked at one example of a research satellite and two scientific topics that it has addressed. There are, of course, many other research satellites that study our atmosphere and have addressed the same and other topics. I hope this will encourage you to learn more about Odin and the other missions that contribute new data and understanding.